So let's analyze a different function. This is not a rational function, but we can still think about graphing this using the same techniques that we've used for the previous two examples. So let's start with analyzing f of x. And the first thing we need to think about is domain. So this one's really interesting because we've got ln of x in the denominator. So if we think about what can x be and what can it not be, we know there's restrictions on the ln function. So anytime we take the ln, that argument, which in this case is just x, has to be greater than 0. So we know that x has to be greater than 0, but we also know that that denominator can't be equal to 0. So let's figure out where it's equal to 0, and then we'll have an issue. We'll know where the issues are. We can rewrite this as an exponential function. The base of the ln function is e. This is your exponent, and that's going to be equal to x. And we know that e to the 0 is equal to 1. So this is where our issue is. So if you think about a number line, has to be bigger than 0 because of that ln function, but 1 is a problem. So our domain is 0 to 1, and then 1 to infinity. Now let's find x-intercepts. To find an x-intercept, we set y equal to 0 and solve. We can multiply both sides by ln of x. So we get x is equal to 0, but we have a problem. Because 0 is not in the domain. So our conclusion is that we don't have any. To find a y-intercept, we would set x equal to 0, but once again, we're going to have a problem. The numerator's fine, but we can't take the ln as 0, which means we don't have any. So we have no x-intercepts, no y-intercepts. Let's look at asymptotes. Do we have any kind of vertical asymptotes? So it seems like we should have a vertical asymptote where that denominator is equal to 0. Which is at 1. But to show that we have a vertical asymptote, we need to see unbounded behavior. So let's look at this a little closer and see whether or not we do. We need to take the limit as x approaches 1. I'm going to come in from the left-hand side of the function. And then I'm going to come in from the right. And we need to know, do we have unbounded behavior? Then we'll go to my calculator. X divided by ln x. I'm going to go to my table. So if I'm coming in 1 from the right, I'm slightly bigger than 1. And you can see how those y values are getting pretty large. So we have unbounded behavior from the right hand side. And we could come in from the left too. I'm getting close to 1 from the left, so I'm looking at 0.9, 0.99, 0.999. So from the left, we're heading to negative infinity. From the right, we're heading to infinity. So we definitely have a vertical asymptote at x equals 1 for sure. But you may also be wondering, do I have 1 at 0? Because that was an issue also, because we can't take the ln of 0. Well, we can discover whether or not we do by looking at that limit again. Now keep in mind, on this side, we have to come in from the right only. This graph doesn't exist to the left of 0 because of the domain restrictions. So let's look at our function here. I'm coming in 0 from the right, so I'm looking at 0.1, 0.01, 0.001, and remember, we're asking, do we have unbounded behavior? Are we heading up to infinity or negative infinity? And in this case, we are not heading up to infinity or negative infinity. We are actually heading to 0. So at 0.1, we're at negative 0.04. At 0.01, we're at negative 0.002. And then we start going in scientific notation, which means we would move this decimal 4 places to the left. So it would be negative 0.0001 there. And then we get even smaller here. So the answer is no, we do not have unbounded behavior. This is actually heading to 0 on that side. So we have one vertical asymptote. Let's look at horizontal asymptotes. To look at horizontal asymptotes, we can't use the regular rules we would use for a rational function because this is not a rational function. So we have to use our calculus definitions. Let's take the limit as x approaches infinity of this function. So if I were to take that limit as I approach infinity, I'm going to have infinity over infinity, which means I need to use L'Hopital's. So I'm going to take the derivative of the top, the derivative of the bottom, and I'm going to reevaluate. I'm going to simplify that complex fraction. That's the same thing as x. And as x gets larger and larger, this is heading to infinity, which means no, we do not have a vertical asymptote. I'm sorry, a horizontal asymptote. So there's all the information for analyzing f of x. We didn't get a whole lot. We just know domain and we know we have a vertical asymptote. So now let's go on to analyze the first derivative. So f of x is equal to x over ln of x. To take that first derivative, we're going to use quotient rule. Quotient rule says it's the bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. So that is equal to the ln of x minus 1 over the ln of x quantity squared. So now let's set this equal to 0. So we're going to have 0 is equal to the ln of x minus 1. 1 is equal to the ln of x. Rewrite that as an exponential. Base is e, exponent's 1, and that's equal to x. So there's our critical number. Now, we also need to know where the derivative is undefined. And that happens at 1. Remember, that was that vertical asymptote that we talked about earlier. If we were to set that denominator equal to 0, take the square root of both sides, rewrite as an exponential, that's where our 1's coming from. So both of those have to go on your sign chart for that first derivative. So f prime of x, those are the only numbers that go on your sign chart. Now, we're not going all the way down to negative infinity here. We can't go below 0. So I've got 1, and then I've got e, and e is about 2.71. So now we're going to test numbers. And remember, this is going into that derivative here. And this is where you may want to use your calculator to type some numbers into that derivative. So x equals 1/2. I got a negative. X equals 2. I got a negative. And then I'm going to substitute in 4. And that gave me a positive. So we know some stuff about concavity here. And where we're increasing and decreasing. So we are increasing from e to infinity. We are decreasing from 0 to 1 and from 1 to e. Keep in mind, 1 is a vertical asymptote. But e, look what's going on. We're decreasing, then we're increasing, which means we have to have a minimum value there. So we have a minimum at x equals e. And to find the y-coordinate, we're going to plug e back into our function. So we're going to have e over the ln of e. The ln of e is 1, so this is at e. And no maximums. So there's everything from the first derivative. Now let's do the second derivative. I'm just going to rewrite that first derivative here so we have it. It was ln of x minus 1 over ln of x squared. Quotient rule. Bottom, derivative of the top, minus top, times derivative of the bottom, and that is a chain rule. Bring the exponent down, subtract 1 from the exponent, take the derivative of the inside. And that's all over the bottom squared. ln of x squared is going to be ln of x to the 4th. Let's see if we can do some factoring. So we could pull out a 1 over x times the ln of x. And that's going to leave us with the ln of x minus 2 times ln of x minus 1 over the ln of x to the 4th. So I factored out the 1 over x's, and I factored out one of these. Let's double check. Everything looks good. So combining some like terms, 1 over x times ln of x times ln of x minus 2 ln of x is minus ln of x. And if I distribute that negative 2, I'm going to get a plus 2 there. So we're going to do some more simplifying. That ln of x is going to reduce there. So I have 1 over x times 2 minus ln of x over the ln of x cubed. Now, I don't like complex fractions. I like to eliminate those. And we can multiply the top and bottom by that least common denominator. As long as you do the same thing to the top and the bottom of the fraction, it's okay in math. So x times 1 over x is going to be 1. So we're going to have 1 times 2 minus ln of x, which is just 2 minus ln of x. And then we're going to have x times ln of x cubed down here. So there is our second derivative. Now we want to set it equal to 0. So we're going to get 2 minus ln of x is equal to 0. 2 is equal to the ln of x. So e squared is equal to x. That's a possible inflection point. We won't know if it's an inflection point until we do that sign chart for the second derivative. So, but also, we also have to think about where it's undefined. F double prime of x is undefined at x equals 1. Remember, that was your vertical asymptote. And that comes from setting that denominator equal to 0. We would get x equals 0, but remember, that's not in the domain. And then we get ln of x to the third is equal to 0. So ln of x is equal to 0. So we get 1. Now, let's put everything on our sign chart. Can't go below 0, so I'm writing that in. So I've got 1, and I've got e squared. And e squared is about 7.4. So we need to test the numbers. And remember, these are going into the second derivative. So I'm going to use my calculator to do this. I'm doing it off screen. So I'm just going to type it in. 2 minus ln of x divided by x times the ln of x to the third. So let's plug in a half. We can plug in 2. And we can plug in maybe none. So at half, I've got a negative when I plugged in 2. I got a positive. And then when I plugged in 4, not 4, I mean none, I got a negative. So concavity, let's see, where can I write that? So we are concave up from 1 to e squared. We are concave down from 0 to 1, and then from e squared on. Now keep in mind, vertical asymptote at 1, so 1 is not an inflection point. However, e squared is an inflection point because we have that change in concavity. So e squared is an inflection point, then y is going to be e squared divided by the ln of e squared. Which is going to be e squared over 2. So now we have all this information, and this has got to go on a graph. So here's my graph. So I pulled all the information from the last couple of pages where we analyzed f of x, f prime of x, and f double prime of x, just so we don't have to flip back and forth. So now let's come up with what this picture is going to look like. So here's my picture. Just going to draw some tick marks here. Now, we know the domains from 0 to 1 and then 1 to infinity, so there's not going to be anything on this part of the graph. We have a vertical asymptote at x equals 1. So there's two pieces to the graph, something in here and then something over here. So let's talk about that something in here first. Now, we didn't have any x or y intercepts, but we know about decreasing and increasing, and we know about concavity. So between 0 and 1, we are decreasing, and we're concave down. So it's going to look like this, decreasing, concave down. We also know the graph starts at 0, but it cannot include 0. That came from the domain. So we would have an open circle there. We do know minimums, a minimum. Draw a few more tick marks there. We have a minimum at EE, and E is about 2.7, so about 2.7, 2.7. So a minimum is going to be right here. And then we have an inflection point at E squared over 2. E squared is about 7.4. E squared over 2 is about 3.7. 1, 2, 3, 4, 5, 6, 7.4, 3.7. So somewhere around here we have an inflection point. So we are decreasing from 1 to E, and then we start increasing. So we're going to have to come down, then come back up, going through that minimum. But we need to include that concavity in here also. We are concave up from 1 to E squared. And remember, E squared is over here at that inflection point. And then we end up being concave down. So, gonna go through there, concave up, and then it's gonna be concave down. So it should look something like that. And if we were to graph this one in our calculator, we would see that that's a pretty good representation of what this graph looks like.